Good morning, everyone. So today we are going to start this course. This course is titled Semiconductor Devices and VLSI Technology. So today I am going to give an introduction about this course. What is this course about? What is the big picture? What are we trying to cover in this course? So let us see the course objective, right? So this is essentially an undergraduate level course, right? So the primary objective is to develop an understanding of semiconductor physics, and using the semiconductor physics, okay, you try to explain, right, or understand the operation of basic 2-terminal and 3-terminal semiconductor devices. So some examples of 2-terminal and 3-terminal semiconductor devices are like PN junction diodes, transistors, right, solar cells. So and also in this course, okay, we introduce you to the unit process, right? Okay, so one is about the device, the other is about how do you manufacture this device, right? So this manufacturing process, it's actually a very complex process, but this complex process can be broken down into different unit process steps, right? So once you understand the unit process steps, right, then you can stitch together these unit process steps to develop different structures and different semiconductor devices. So that is what being done in a semiconductor fabrication plant. Okay, so they have different unit process steps. So in the same plant, okay, you can run different products, right? For example, the different transistors with the different technologies, right? Those are all. So here we will see. Then finally, we will see how these unit process steps are stitched together to form like the process integration, that is known as a process integration, and we will see the process integration for maybe two devices like diodes and a CMOS transistor. Now, let us take a very high level view, right. So, this course is titled Semiconductor Device and VLSI Technology. This is an engineering course. Okay, let us try to start with the definition of what is technology, right. What is technology? So, in technology, right, okay, so this technology need not be electrical technology or computer technology, right. So, this is broadly what is this technology. So, here our goal is to create, right, okay, develop knowledge and instruments, right, based on that. So, instruments or these gadgets or something, okay, the humans, okay, we try to accomplish some purpose of the life, right. It could be a simple, it could be very ubiquitous like this smartphone, or it could be television, all those things, okay, those are all products of technology. So, these are artifacts which are not readily available in nature, right. So, for example, we say that, okay, this we don't call like a sand or something like a technology, right. So in order to create these products, right, we take the raw materials, right, and we do a lot of material processing. Okay, we do a lot of material processing and we convert into a useful product, right. So this kind of a processing, it could be material, it could be information, it could be energy, right. So we may be harvesting, suppose in the case of solar cell or something, okay, we may be harvesting energy from one form, okay, we may be converting into another form, right. So those are all, so you do material, information and energy processing in all these gadgets. So I mentioned about the information processing, but this is one thing which people tend to forget. Okay, so these non-material forms of energy technology, for example, information technology, all right, they are actually completely useless. Okay, without physical infrastructure on which to use it, right. So suppose you are doing information technology, okay, you require physical infrastructure to do the processing, right, information processing. Or if you want to do information storage or information transfer, right, you require physical devices, right, to do this information technology. If you look at, if you step back and look at the history of technology, right, okay, so normally when we ask students or maybe a common man, okay, what is technology, one common definition is, okay, it is applied science, right. But if you look at the history of technology, that definition, right, that is mostly true from maybe like the middle of the 19th century onwards, right, mostly in 20th century and 21st century. So before that, okay, if you look at the history of technology, the technology was there, right, even without people were using this kind of a gadgets, right, without knowing the underlying science. For example, a simple example is like the for the spectacles, right? The spectacles, people know about the spectacles. Okay, they like people used to grind glass and to make spectacles, but they didn't know anything about the theory of optics. Okay, there was no well developed theory of optics, right? Other important thing is that, okay, the technology, okay, that actually helps in the progress of science, right? So it's not like it's like a linear chain. Okay, first science, then comes technology. Okay, so it is like there's a complex interplay between science and technology. So any big science projects, for example, like the Large Hadron Collider, or for example the Hubble telescope. Okay, so these are, that requires a lot of technology, right? So that is a two simple examples where the technology is aiding in the progress of science. So if you look at the history of technology, there are different technological products, different technology, right? So right now we say that, okay, why technology is important? That is because, okay, it is important for the economic growth of nations, right? But if you look at the history of, if you have seen, if you have read about the history of nations, okay, so every nation, or okay, people may think that, okay, they have had a golden age before in the past, right? So I think there were different, okay, whether in India, China, or in Holland and all. Okay, so they had, it's like the brief periods of prosperity, right? But after, what happens is that, okay, that it stayed only for some time, then it died down, right? But if you look at the history of technology, for example, this is a very interesting chart, right? Interesting chart. Essentially, they are plotting many metrics, okay, many metrics like life expectancy, per capita GDP, percentage of people living in extreme poverty, energy capture, I think war making capacity, number of people living in democracy and all. Okay, say that, okay, so till around 1700s or something, okay, till in the 18th century, okay, it was not, there was not much, okay, there were no big trends, right, if you look at history. Then in the 18th and 19th century, okay, if you look at all these parameters, okay, you see some kind of a hockey stick kind of a this thing, okay, suddenly people, so you can see a large increase, improvement in these metrics. So what has happened is that, okay, so what, that is the time of the industrial revolution. So why industrial revolution is very important is that, okay, so that is when, okay, the nations or countries, they started to seeing sustained economic growth. Okay, so it's not like the old golden age periods, okay, where the growth peters out after some time, right? So here we see countries having economic growth based on technological progress. The first nation, okay, which had this kind of a progress was actually the Great Britain. So this if you look at this one, okay, so this is one way, okay, one very simplistic way of looking at this chart. Okay, one can comment that everything was awful for a very long time, and then industrial revolution happened. That is a very simplistic way of looking at it, but that is the picture one can get by looking at this chart. And also, if you look at the various technologies, okay, so we develop technology to solve some, there is a need, or there is a problem, right? For example, we have spectacles, okay, that is to solve the eyesight, right? Otherwise, for example, a person like me, okay, if I were living in maybe like the 12th century or 13th century or something, okay, so at this age, okay, I cannot read any more books, right? Because unless if you don't have spectacles, you cannot read books. Okay, so this is actually a big boon, right? So for example, the spectacles were introduced to solve the problem of the eyesight. But if you look at there are other technologies, okay, where they might have introduced that technology for one particular, to solve some issue. But finally, what has happened is that they found out that there are many other users, okay, where other areas also can adapt this technology and they can make further progress. So economic historians, they call such technologies as general purpose technologies. So three classic examples of general purpose technologies are actually steam engine, electricity, and semiconductors. Let's see why steam engine. Okay, the steam engine, if you look at the history of technology, because the steam engine was introduced essentially to pump water from the tin mines, okay, or the copper mines in England. Okay, so they used to flood. Okay, so they need to pump the water out of that. And there were you might have heard about the name James Watt. Okay, so James Watt, okay, if you are interested in QSers or something, okay, typically you might have learned like James Watt invented the steam engine. But that actually, James Watt didn't invent the steam engine. Actually, what James Watt did is that he improved the steam engine. He improved the efficiency of the steam engine, right? So Initially the steam engine was used in mining, right? Then okay, so when they improved the steam engine, it was used in textiles. Then once they made the steam engine very compact, okay, you could put it on a locomotive. That's how the railways have started. Then you can introduce then you can power the entire factories using steam engine. So you can see the proliferation of steam engine. Okay, it is they were, so the steam engine was used in areas which were not initially, so initially it was applied in mining, but you can see it proliferated, right? The same thing with electricity, right? Electricity, the original purpose of the electricity was actually entertainment. Okay, so the original application of the people in the 18th century in Europe, okay, they were mostly, the electricity was used initially for entertainment purpose. Later, okay, it was developed for lighting, motor applications, now even in electric vehicles. So the same thing for semiconductors. Okay, if you look at the history of semiconductors, okay, initially it was mostly used in some airborne applications, right? But later for military applications. Now later it was used in industrial, then computer, then all this AI, everything is built upon this advancement in semiconductors. Now let us see what are semiconductors, right? So that is this course is about semiconductors. So some of you have some idea about semiconductors. Okay, if I ask somebody about the semiconductors, okay, normal definition about semiconductors is that these materials, okay, these are materials whose resistivity or conductivity lies between metals and insulators. That's a good definition. But much more useful definition is that what is given here. These are materials whose conductivity can be modulated. Okay, that is the important speciality of semiconductors. Okay, their conductivity or resistivity can be modulated over a wide range, right, by using some external means. Okay, for example, the external means could be doping, it could be light, right? You shine light, it changes the conductivity, or applying by electric field. So when you talk about semiconductors, okay, if you read literature, or for example industry magazines or newspapers or business articles, okay, when they talk about semiconductors, they don't mean like the raw semiconducting material, okay, the pure semiconductor, right? Actually what they mean is that actually furnished products. Okay, so when they, what semiconductors means is mostly integrated circuits. So integrated circuits is the biggest semiconductor product, okay, largest category of semiconductor product. So they contain billions of transistors, okay, and they perform very high level of functions, right? And there are other class of semiconductors known as discrete semiconductors. Okay, they contain only one or few transistors and they perform simple function. So for example, like power applications. Okay, power applications, they are mostly discrete and they may contain only very few transistors because they have to handle large amounts of current and voltages. So truly semiconductors, they are actually the brains of modern electronic systems, right? So if you look at the bill of materials of any electronic system, right? Okay, typically around 30 to 40%. Okay, the price is actually due to semiconductors. So the semiconductors, okay, they enable advances in all areas, right? To the communications, computing, healthcare, defense, transportation, clean energy. And okay, if you look at the modern day drivers, okay, the current day the drivers of the semiconductors, okay, they are mostly like the AI chips, the chips for the servers, the data center, all those things. So this is a beautiful quote, okay, from the Shanghai Museum of Urban Development. So the semiconductors are for information society what grain was there for the agrarian society, and iron and steel for the industrial society. Now let us take a big picture of, okay, about the semiconductor industry. So as I mentioned here, the semiconductors actually, they are not just raw materials. Okay, they are actually sophisticated products, okay, made by a collective optimization effort. Okay, so a lot of people had to work. Okay, it is not possible for one person to create a semiconductor product, right? So, so all the way from software to materials. Okay, so if you take any chip, okay, so that design and manufacturing. Okay, that there's a lot of optimization effort which happens across different companies. People within different companies, they may be sitting in different geographical location, right? This is an entirely, it's a complex process. Okay, finally it is made in a highly specialized manufacturing facility, what we call as a fabs or the fabrication plants. So typical semiconductor products are processors. Okay, it could be for your computing or for your smartphone. DRAM, there is a memory, the sensors, flash memory, discrete power devices, etc. Right. So, this is what I call as the end-to-end optimization. So, any semiconductor product, okay, so it starts with materials, okay. So, the materials, so using materials we make structures, right. So, this is very similar to what is done in civil engineering, right. You may use concrete to make structures, right, but that is a very macro level structure. So, here in the semiconductors, okay, we make structures actually which are even smaller than the size of a virus actually. So, using structures we make devices, using devices you assemble, you interconnect the devices to make circuits. So, circuits you have a lot of circuits to define a high level architecture, then you may put it in a package, okay, then it will be programmable, right. So, that is where the software aspect comes from. So, if you look at the entire semiconductor industry, it will look like something like an inverted pyramid, okay. So, this is inverted pyramid. So, in order to make a semiconductor device, so this industry is somewhere around $600 billion. So, what we require is you require two things. Okay, one is you require some these days. Okay, these are not done using pen and paper. So, you require sophisticated computer aided design tools. Okay, so that is what we known as the EDA. This is an electronic design automation, right? And you have some intellectual properties, right? So, these are, and using this, and okay, we require, right. So, finally, what is your idea which is there in the design phase, okay, this needs to be translated to the surface of the wafer, right. So, we need a lot of materials and we need a lot of equipment, okay. So, so we need equipment. So, using these two, okay, we create semiconductor devices, and these semiconductor devices are, who uses these semiconductor devices? So, those are those are used by makers of electronic systems, right. And these electronic systems, okay, they will be finally used in other tech industries. So, for example, if you look at materials, okay, at the bottom of the pyramid, okay, you have various vendors here, okay, they may sell wafers, okay, they may sell specialty gases, all those things. These are equipment makers, okay, they sell equipments, okay, which are being used by companies like TSMC or Intel to make chips. And these are the EDA vendors, okay, they sell IP and they sell tools, okay, these are the CAD tools, right. Then once you come to the companies which make the chip, okay, there are two types of companies, okay, one is actually known as integrated device manufacturers, okay, they make the chips and they sell the chips, right. So, they will do design as well as manufacturing. Then there are other companies which are known as foundries, okay, they only do contract manufacturing. They don't, so they may, for example, like the TSMC, right, that is a biggest foundry, they get a design from AMD or Qualcomm or NVIDIA, right. So, they convert their design into a product and they will give the chip back to them. So, they do not sell any chips, they only do contract manufacturing. Then there are other companies which do only assembly, testing and packaging. So, finally, these chips, okay, they are used by these tech companies, okay, for example, like Google, Apple, Amazon, Facebook, Apple, Microsoft and all those things, right. So, it could be used in some information industry, broadcasting industry, all other. Now, let us see where are the chips all these devices being used, okay. For if you look at this sector, okay, these are the main products, okay, it could be for logic applications, for memory applications, it could be some power and analog, then optoelectronics and sensors, right. So, the biggest application is actually, the main driver is actually smartphones, okay, the smartphones is the biggest driver. Then what you have is actually your desktop computers and servers, right. So, this is for a data center, right. And this is, okay, so you can see there are applications, okay, this is in electric vehicles, and then these are all industrial or industrial purpose. Now, let us take a quick look at the history of these semiconducting devices. So, even before semiconductors, okay, we have been using information processing machines, okay. So, this is two classic examples of information processing machine. This is a Jacquard's loom, okay, this is actually a loom, okay, this is to print the textile, okay. So, in the okay, so what was his innovation is that, okay, he used this kind of punch cards, okay. So, you can code the design in this punch card, okay, so then it will read, okay, that it will create a pattern here, right. So, this was done, okay, this was done in the early 19th century. A similar concept was used by Hermann Hollerith. Okay, so this is to okay, the same punch cards, you can see the punch cards here. Okay, this was used first to do the US census, right. So then that company actually later actually became the IBM, the current IBM, the same company. Now moving a little more. Okay, so here is legendary. Okay, all electrical engineers know his name. Okay, this is Claude Shannon. So before Claude Shannon became famous for his communication theory, okay, he was a master's student at MIT. Then Shannon showed the Boolean algebra. Okay, so at that time the Boolean algebra, it was there. Okay, George Boole came up with this Boolean algebra. There was not much application. So Shannon showed that okay, you can use Boolean algebra to design digital circuits with on-off relays. Okay, that was in 1938. Right. So the Shannon's work is actually considered as the most important master's thesis ever written. So this work is actually normally it is being clouded or being overshadowed by his later communications theory work. So this is a computer from University of Penn State. It is ENIAC. Okay, it stands for Electronic Numerical Integrator and Calculator. So this is a computer which was based on vacuum tubes. Okay, so if you look at this one, this is a colossal machine. Okay, it weighed around 30 tons. It had 18,000 vacuum tubes, right. It consumes 140 kilowatts of power. It needed a 1800 square feet, and what finally it can do is that okay, it can do a decimal multiplication in 3 milliseconds. Okay, definitely it is much faster than any human computer. Now let us see some of the early developments of the semiconductor devices. So most of the initial work, okay, that was done in actually the Bell Labs. Okay, so Bell Labs was a research arm of the AT&T. So AT&T at that time had a monopoly of the telecommunications market, right. So Mervyn Kelly, who was the vice president of Bell Labs, okay, he had this vision that okay, whether at that time all the telephone exchanges in the of the AT&T, okay, they were using electromechanical relays, right. So what Kelly proposed was that why can't we replace these electromechanical relays with the solid state devices, right. So that will improve the reliability, it may make it even smaller, right. So the main idea of the transistor, okay, it was proposed by William Shockley, right. That is the idea of junction transistor. So he proposed this in 1948. So at that time there was another idea also, that is actually known as point contact transistor, which was developed by Brattain and John Bardeen. But the junction transistor actually it is actually the manufacturable and reliable solution. That is okay, what Shockley's this one is that he actually developed the theory and operation of this transistor even before a single junction transistor was made. So finally, the what actually went into production was a junction transistor. Okay, so and at that time the junction transistor used to look like something like this one. Okay, so this is the emitter region, this is the base region, this is the collector region. So initially the transistor was mainly used in some consumer applications, something like it started with hearing aids, then they started using in computers, then for example Sony used the transistor to create a pocket radio, right. But the military was interested in these transistors because they found out that okay, you can reduce the weight and size of these airborne systems, right, if you use these transistors. Right. So, but the problem was that the existing transistor could not meet the reliability specs of the Minuteman I intercontinental ballistic missile. So, what at that time, okay, so one of the first companies who was working on semiconductors was the Fairchild Semiconductor. So John Horney, okay, he came up with this idea of planar process. Okay, so rather than he found out that okay, the issue is that okay, you have all these exposed junction, right. You will see later in the course about PN junctions. Okay, a region between a P-type semiconductor and an N-type semiconductor, you have something known as a junction is there. So if you leave the junction exposed, okay, so it will affect the reliability, leakage current, and all those things. So Horney's idea was to don't leave this exposed junction, you passivate it with the silicon dioxide. So this is the idea of planar process, right. So this planar process is actually considered as the most valuable semiconductor patent, right. So this actually made the integrated circuit possible. Now let us see how it was done. So, this is okay, this slide is slightly like a solid state of progress. So, it is literally a solid. So, you can, this is a Horny's planar, right, the planar transistor. So, as we saw, this was the initial, this transistor actually it used to be known as a mesa transistor. So, the why the mesa is okay, because it looks like a small plateau, right. So, then this is a planar transistor. So, Horny was working at Fairchild Semiconductor. So, his boss was actually Robert Noyce, okay, who later founded and became the CEO of Intel. So, once Horny came up with this idea, so Robert Noyce extended this one, right? Extended this one. He said that okay, you can make integrated circuits. So, you can make more circuits, okay, because right now your top surface is covered with oxide, right? Then you can lay metal wiring and you can interconnect the transistors. So, that is what these figures are from Robert Noyce's patent. Then finally, what the Fairchild, okay, they put together a team, right. So, this was just an idea, there was no, they filed a patent, they finally put together a team, okay. So, that is the Fairchild's micrologic team. So, it consists of these members, okay. So, these members, and they made the first integrated circuit, right. So, this is the, so you can see this is a US coin, 1 dime, and this was the first integrated circuit. So, this so now this is another interesting thing is that okay, so you can see the propagation of ideas, okay. So, this idea, this is the initial, the Horny's idea of planar transistor, that was modified and used to create the pattern for the integrated circuit. But if you look at the team members, okay, so you don't see neither Horny or nor Robert Noyce, okay, in this production team, right. So, this is typically this what happens typically in an engineering product development, right. Somebody might have created an idea and somebody later will actually make it a reality. So, now let us see, okay, so at that time of the integrated circuit, okay, actually that was a very expensive product, okay. So, and also the complexity of products, okay, it was not very complex. So, you could still buy discrete transistors and you can assemble it, right. So, the initial adopters of integrated circuits, okay, these were the only two customers who could pay top dollar to get integrated circuits. Okay, so the two main customers was, okay, this is for the Minuteman seconds, the second Minuteman in the ICBM. So, for this actually the Texas Instruments supplied the ICs, and other important, if this thing is the Apollo guidance computer, right. This is a guidance computer which put Neil Armstrong and his buddies into moon, right. So, the Fairchild supplied the ICs, okay. So, if you look at the guidance computer, it had only 5,600 logic gates. So, the initial the main customer, right. So, it came with this one, okay. So, so the airborne components, okay, the aerospace industry, that is all, they are always worried about the weight, right, and also the reliability. So, if you could miniaturize the airborne components, okay, that was one of the main motivation, right. You could reduce the burden on the rocket propulsion, right. You can reduce the weight of the components, the payload weight you can reduce. Right. At that time, the US was lagging behind the USSR on the rocket propulsion. So, even with a slightly inferior rocket propulsion technology, if you reduce the payload weight, you can still put things into the orbit. Now, let us go, okay, that was in 1960s, okay, let us move fast forward to present, okay, what is the state of the art, right. So, this is an example some of you might have seen, okay, this is a Cerebrus wafer scale engine, okay, it is used for AI applications, okay. So, this it's like an entire wafer is a chip actually. So, it has 4 trillion transistors, right, 4 trillion, okay, that is 4 into 10 to the power of 12, right, transistors. It has 44 GB memory, it has 900,000 cores, and the area is around 46,000 millimeter square, right. So, not everybody may be using in their day to day life the Cerebrus, okay. For example, this is the smartphone, okay, from last year, iPhone 16, so which you can hold in your hand, right. So, the chip, so it contains 16 billion transistors in 100 mm square, right. So, you can see earlier I mentioned about you are making structures like similar to civil engineering, right. So, within this area you are making small structures to make 16 billion transistors. So, if you look at any single smartphone today, right, which you can hold in your hand, that has far more computing power than the computers used by NASA to land a person on the moon. Now, let us see how this was achieved, right. So, essentially this was achieved by making transistors smaller and smaller and smaller, right. For this is an example, this is a plot from IEEE Spectrum magazine, okay, to April 2015. So it shows the progress from 1955 to 2014, okay, at that time. So if you look at, okay, this is the chart, okay, this is a chart here. This is, if you look at the number of transistors made per year, okay, so that is the made per year. So you can see it is growing, right. So it's from one here, okay, so this is all the way to like sorry, this is here, right. So we are going all the way to something like more than 10 to the power of 23 transistors, okay. We are making large number of transistors, right. So you won't be able to see them because they are so small, right. So if you put your hand in your pocket and if there is a cell phone there, okay, there are already some couple of billions of transistors sitting in your pocket. Another phenomenal aspect is that about the price per transistor. The price per transistor has been constantly falling, okay. So this unit is actually billionth of a dollar, right. So you can see the price per transistor has fallen like a 10 orders of magnitude, right. This is something which has never happened in the history of technology or in economics, right. The price of something has fallen 10 orders of magnitude. So truly the transistors, they are actually the most abundant man-made object, right? If you count each and every transistor, okay, we are making around 10 to the power of 23, okay. So here is something we can say which is very close to the Avogadro number, right? That many transistors we are making every year, right. And if you want to appreciate this number, right, if you want to appreciate this number, okay, you might have heard about the story about a wise man, okay. He went and went to play with the chess with the king, right. The king promised that, okay, if the wise person wins the game, he will reward him like putting one grain on the sand, one grain of rice on the first square, then two on the second, for the third, like, okay, it goes in the geometric progression, right. And so if you do the math, actually the number of grains needed to honor this promise is actually 1.8 into 10 to the power of 19. So if you look at the entire worldwide rice production, actually that is actually smaller than this one. On the other hand, okay, if the king was, if it is a modern day king, and if he or she had promised that, okay, I can give you in terms of transistors, okay, maybe he could have honored this promise. So finally, when you do scaling, okay, scaling means, okay, you are making this transistor smaller and smaller, right. So what happens, this is a beautiful quote from George Gilder in Microcosm, his book. So he's saying that everything gets better as it gets smaller, right. And other important thing is that they get cooler as it gets faster. This is very contradictory. If you look at other mechanical systems or something, right, if you run it fast, okay, it may get hotter and hotter, right. And also it gets cheaper, right, it gets cheaper, right, and it becomes more valuable. So the technology, okay, the technology to make all these transistors, okay, the modern day chip, okay, that is what we call as a modern semiconductor manufacturing. Actually, it is the most sophisticated and high unforgiving high volume production technology, right. You can compare it with any high volume manufacturing, right. Nothing comes closer to semiconductor manufacturing, right, in the amount of precision and all these things which is required. So if you just to give some pictures about what's the progress we have. So earlier we saw the progress in the logic, right. So now let us see the progress in the information storage, right. So this is high density. So this is a picture from 1956, right. So here, so this is what is shown here is an IBM's hard disk, okay. This is a 5 megabyte hard disk, right. But if you look at storage right now, so this is a solid state drive from Samsung, okay. It is for 30 terabytes, right. So you can see, so this order of that is actually 10 to the power of 6, right, mega versus tera. And also if you look at, right, some of these solid state drives, okay, they use a product, the semiconductor device actually 3D NAND, okay. So this technology, okay, so this is like a, if you try to visualize, this is insane, okay. So if you hold your thumb, right, of your in this area of your nail, okay, thumbnail, okay, you may be drilling something like a billions of holes, right. So and you have to do it repeatedly without fail. This is also another, this is information storage. This is about a RAM, right. So in the 1950s, okay, so the computers, okay, the main memory, the main memory of the computer was actually magnetic core memory. So this is a magnetic core memory from 1964, right. So this is nothing but, okay, if you look at the picture here, this is like a matrix, okay. So and you have a magnetic bead sitting here, right. So we could program by changing the magnetization of that magnetic bead. So this is okay. This is so if you might suppose if you have done programming or something, okay, you might have encountered this error message like a core dumped. Okay, so this is actually comes from these days. Okay, because we used to use magnetic core memory. So in 1970s, when Intel was formed, one of their first product was actually a DRAM. Okay, so it's a 1 kilobit DRAM. So this chip actually killed the magnetic core business, right? So after that, okay, nobody is using magnetic core. Everybody switched from magnetic memories. Okay, at least in the case of the RAM, right? The RAM for computers. Okay, they switch from magnetic memories to semiconductor memories. So this is a product from Samsung. Okay, from 2021. Or this is a 512 gigabyte DIMM module. So you can see, right? Okay, so if you look at from here, essentially what we are doing is that we are making semiconductor devices smaller and smaller, right. So this DRAM is nothing but a transistor with a capacitor. So this is a transistor, this is a capacitor, right. So we can see different, so this is the evolution of the DRAM, right. So if you want to make the density, if you want to increase the density, you want to make this devices smaller and smaller. So you need to device and process engineers, they need to come up with various innovations how you can make the bit cell smaller and smaller. So you may be wondering who needs so much memory, right? So much memory. So for example, this is a chart from this one. So every minute of the day, okay, everybody is generating lots of data, right? So here, whether it through an email application, through Google, text, Facebook, all those things, whether YouTube videos like this one, right? So as a user, right, you may be wondering, okay, where you are generating all this data, where is this data being stored? Okay, so we say that cloud or something. Okay, so that is what. Okay, so the cloud, okay, it is not like some kind of a vaporware, right? It's actually a physical product. Okay, it could be a semiconductor memory or some other disk memory. So that is being all stored there, right? So the global data generated annually. So it's a projection is that, okay, in 2025, okay, we may need a 180 zettabytes. Okay, zettabyte is around 10 to the power of 21, right? So you're generating a lot of data. You need, okay, so you need to move this data. So that is information transfer. You may have to process the data, that is information processing, and you may have to store the data, that is information storage. So in all these three verticals, okay, you require semiconductor devices. Now, so I gave you a very short, okay, quick introduction about the history of semiconductors. Okay, now let's see what we have learned from the history. Right. So here is this is an advertisement, one of my favorite advertisement. Okay, so this is from early 1950s, right? So this advertisement is given by General Electric, the GE company. So here, what is the advertisement is that, okay, so the one person is looking at this one. Okay, there are two products. Okay, these are transistors, right? These are the discrete transistor, and this is a vacuum tube. Okay. If you look at the price, this is actually $2 per transistor, and this is only $1.15, right? And the question is actually, must you pay the high price of miniaturization? Okay, that's a provocative question. Okay, why do you want to spend more amount? Okay, for transistors, why can't we stick with vacuum tubes, right? So if the entire industry and entire consumers, okay, had they said that, okay, we don't want a high price solution, okay, we will stick with this one, okay, then what would have happened, right? Essentially, most of the electronic systems we see today, right, okay, and it includes this electronic system through which you are watching this video, right? It would not have existed, right? If it had existed, because it's energy per operation, right? How much energy is being used for one operation? So the quantity is something like, okay, so operations, for example, if you are using a floating point operation or something, how much energy is needed, right? Or the density. We saw the core memory, that's a 4 KB memory, and you have like now you have like gigabytes and terabytes of memory. And what kind of functionality? You see, you have this modern day smartphone. Okay, so it is not only used to make calls, right? That is the purpose of the old phones in 80s and 90s, right? So it is a much more, it's like a mini computer, it's like a mini supercomputer in your hand, right? and what cost, right? So, if there were no transistors and no monolithic integrated circuits, okay, so the electronic systems would have been totally different. So, the large scale integration of billions of devices, right? We saw that the Apple's that iPhone 16 contains around 10 billion transistors, right? So, such kind of a phenomenal integration, right? Putting 10 billion components, right? That is impossible with other states of matter, right? If you use liquid or vapor or something, right? So, that is possible only with solid state devices. So, if you look at the history, okay, we saw that initially it was being used, driven by aerospace industry and military industry, then it became industrial application, then computer, PC, and modern day the technology drivers of semiconductor industry, they are actually smartphones, then high performance computing, for example, the AI chips and the chips which are going into the data centers, they are actually driving the technology. And also there are other applications also, electric vehicles. Okay, so if you look at an electric vehicle, it requires a lot of semiconductors. And also technology and semiconductors, okay, they intruded in other places, right? For example, like medicine, okay, in the middle of the 20th century or something, okay, if you look at medicine, okay, there are not many technological products needed for medicine, okay, and we have started going to energy generation, okay, all the renewables, okay, if you want to do a transition from fossil fuels to renewable industry, okay, so whether it's a wind generation or based on solar cell or electric vehicles, okay, you require a lot of semiconductors. All right. So, having said all these things, okay, let's come back. Okay, what is being planned in this course? Okay, so this course is structured into 4 modules. Okay, module 1, module 2, module 3, module 4. These are roughly the number of hours which is being planned for each module, right? So, in the first module, okay, we discuss about something about the basic semiconductor physics, right? And next we take the first device, okay, that is about the PN junction. Okay, so in this course, okay, there are 2 main devices. Okay, one is a PN junction, other is a MOS transistor, right? So there's a lot of thrust given on these 2 devices. Okay, so if you understand these 2 devices, you can go and you can learn on your own. Okay, I am saying that, okay, if you have understood this properly, you can learn on your own other semiconductor device also. So that is why so the module 2 is entirely devoted to PN junctions, module 3 is entirely devoted to MOS transistors. And the last module, okay, it is about manufacturing, right? So in this module, okay, you will see about the structure of PN junction, structure of MOS transistors. In the last module, we will see how do you make that structure, right? That is very important, right? That is because if you look at the world, modern world, okay, there are only handful of companies, okay, so the number of companies actually maybe even lesser than the number of fingers on my palm. So they only have this know-how to make the advanced chip, right? So we will see what are the basic unit process steps, and we will see the process fabrication process flow of a PN junction diode and a MOSFET. So this is a big picture. Okay, so we will see first how or why semiconductors are different from metals and insulators, right? Then we will discuss about, okay, so if you want to know about semiconductors, then you have to decide, okay, how do you find the electron concentration in semiconductors? Okay, first we discuss about the equilibrium. Okay, so equilibrium is that you don't apply a voltage or current on this one. Okay, it is under thermodynamic equilibrium with its surroundings. Okay, so first, then what we relax this condition. Okay, we apply a perturbation to the system. Okay, we may apply light, we may apply voltage or something. Okay, then what happens to the carrier concentration inside the semiconductor? Then we derive simple IV relationship. There is a current voltage relationship, and we try to explain the operation of the basic devices, right? Then we will see, okay, how do you manufacture these devices and ICs. Then one important aspect of this course is also, right, okay, how do you model? Okay, that is so how do you model these devices, right? So yeah, we come up with some simple models. Okay, these models are being used by circuit designers, right? So the circuit designers may treat this as a black box. Okay, but how do you get these models? Once you have the devices, we will see, especially in the case of MOSFETs, right? Okay, we saw that, okay, the initial in the single large device in 1950s. Okay, we have made the size of the MOSFET so small, right? So small. Okay, how do you actually do that thing? Okay, whether we can go ahead with simply reducing the size, right? if you can simply reduce the size, okay, actually what happens, the device performance actually worsens, right? So you need to come up with lot of tricks and innovations, right? How to make the device smaller, how to make it faster, and how to make it cheaper. So these are the resources, these are the textbooks. Okay, so here I have listed 2 books for semiconductor devices and 2 books for semiconductor technology, right? I strongly prefer, okay, this is an introductory book. Okay, some of you may have already seen this book, but I strongly recommend these 2 books. Okay, these are excellent textbooks. Okay, one on devices and other on semiconductor manufacturing. This is finally I want to leave you with this one. Okay, so this is how this course is different from other courses. First of all, this is an engineering course. Okay, this is not like a pure science course, right? And the real engineering, right? Real engineering, if you have worked with some design or something, okay, so yeah, it involves the art of making approximations, right? And decisions on incomplete data. This is true for any engineering, whether it's an electrical, mechanical, right? So you have to make, because you will be doing design. Okay, for example, design is an important aspect of engineering. You have to design under a lot of trade-offs. Okay, so you cannot meet everything, right? So although we see that, okay, the modern semiconductor devices, okay, they are built actually on modern electronics is actually built on modern physics. Okay, this is not a pure physics course. And also this is, okay, you will see a lot of formula and all, right? Okay, this is not like a pure mathematical course which you can you need to use only pure logic and abstract mathematics, right? So that is why you can see you need to learn about the art of making approximations. And also it is not like compartmentalized course. Okay, we saw there are 4 modules. Okay, it's not like you can skip one module. Okay, you can concentrate on another module. Okay, the later modules can be understood without, it's not like you can understand the later modules without learning the previous modules. Other important thing is, this thing is that students normally forget about this one, is that, okay, so you need to have a sense of numbers. Okay, we will see different physical quantities, whether it's current or voltage or field or the number of atoms or number of electrons or those things, right? You should have a sense of numbers, right? And also you need to, okay, so if you are expressing a physical quantity in using some units, okay, whether that number makes sense or wrong. Okay, for example, if you did a calculation, if you come up with a number of electrons or number of atoms in something like a 10 to the power of 80 or something. Okay, that is, okay, so okay, if you look at, okay, so even the entire universe may not have that much number of atoms. Okay, so that is why you should have a sense of numbers, or whether if you got some number, okay, whether you are doing some calculation using pen and paper, or you run a calculation using computers, right? Whether the numbers you got, whether the numbers you have got, whether it makes sense or sense or not. So if you are somebody who is more interested in the history of electrical engineering and semiconductors, okay, I recommend these 2 videos. Okay, if you go to my web page here, right, you go under, there are 2 semi-popular talks. I recommend you to watch these 2 talks. Okay, one is about the history of electrical engineering and other is about the history of semiconductor devices. It's not mandatory, it's only if you are interested in this one. So from the next class onwards, okay, we are going to start the regular lectures, right? So and I also recommend you to, once you finish the course, okay, I recommend you to come back to this first lecture, right, and see, okay, whether whether your expectations met with what we have told in the first lecture, right? So that again, it gives you like because in the later classes, okay, we are going to take a deep dive into the semiconductor device. Okay, you will see all this physics and all those equations and all, but you should never lose the sight of this big picture. Okay, so that is why if you are ever losing, if you think you are losing the sight of the big picture, you can always come back to this first lecture on this introduction. All right, thank you.